Bismillah ar-Rahman ar-Rahim. We are interested in this summation n from minus infinity to infinity e to the minus pi n squared. It does not seem that there is a straightforward way to compute this summation here. We will start by doing something that is seemingly unrelated, but will eventually lead to the solution. Our starting point is the arithmetic mean, geometric mean iterations. Suppose that we have two positive real numbers, and without loss of generality, let's assume that a is greater than or equal to b. We start our iterations by setting a0 equal to a and b0 equal to b. Then in the first iteration, we have a1, which is the arithmetic mean of a and b, a plus b over 2. b1 is the geometric mean of a and b. So a1 is a0 plus b0 over 2, and b1 is the square root of a0, b0. Now we have two real numbers, a1 and b1, and we do this again. a2 is a1 plus b1 over 2, and b2 is the square root, of course I mean the positive square root of a1, b1. In the nth iteration, an plus 1 is the arithmetic mean of an and bn, and bn plus 1 is the geometric mean. Note that by the arithmetic mean geometric mean inequality, we are sure that at each iteration, an is greater than or equal to bn. This can also be seen from the fact that if we have non-negative real numbers c and d, then the square root of c minus the square root of d squared, this is the square of a real number, so this is greater than or equal to 0. If we expand, then c plus d minus 2 square root cd is greater than or equal to 0. Rearranging the terms, we have c plus d over 2 is greater than or equal to the square root of cd. In each iteration, we compute the arithmetic mean and the geometric mean, so an plus 1 is greater than or equal to bn plus 1. This inequality, an is greater than or equal to bn, is true for every non-negative integer n. The a sequence an, is non-increasing. Why is this? an plus 1 is the arithmetic mean of an and bn. Now we know that bn is less than or equal to an. So this an plus bn over 2 is less than or equal to an plus an divided by 2. an plus 1 is less than or equal to an, and this is true for every non-negative integer n. Sequence a is a non-increasing sequence. What about sequence b? bn plus 1 is the square root of an bn. We know that an is greater than or equal to bn. This is greater than or equal to, and we can replace an by bn, and then we have bn here. So bn plus 1 is greater than or equal to bn. Sequence b is a non-decreasing sequence. If this is b and this is a on the number line, so this is a0 and this is b0, then a1 is less than or equal to a0, b1 is greater than or equal to b0, and a1 is greater than or equal to b1. a2 is less than or equal to a1, b2 is greater than or equal to b1, and a2 is greater than or equal to b2, and so on and so forth. Let's take this inequality and multiply both sides by minus 1. So we have minus bn plus 1 is less than or equal to minus bn. Add an plus 1 to both sides. We have an plus 1 minus bn plus 1 is less than or equal to an plus 1 minus bn. an plus 1 is equal to an plus bn over 2 minus bn. We can take 1/2 as a common factor. Then we have an plus bn minus 2bn. Now the inequality that we obtain is an plus 1 minus bn plus 1 is less than or equal to 1/2 times an minus bn. The difference between an plus 1 and bn plus 1 is less than or equal to 1/2 the difference between an and bn. This inequality means that a1 minus b1, when we use n equal to 0, a1 minus b1 is less than or equal to 1/2 a0 minus b0. This inequality also says that a2 minus b2 is less than or equal to 1/2 a1 minus b1, which in turn is less than or equal to 1/2 a0 minus b0. This means that a2 minus b2 is less than or equal to 1/4 times a0 minus b0. a0 is a and b0 is b, and so on. We have this inequality that an minus bn, and this is a non-negative quantity, is less than or equal to 2 to the minus n times a minus b. The difference between an and bn is upper bounded by the difference between a and b times this 2 to the power minus n. Our conclusions are as follows. Sequence an is monotonically non-increasing. It is bounded below. So here we have a, and then we have a1, then a2, and here we have b. Every element in sequence an is lower bounded by b, is some positive real number, less than or equal to a. Sequence bn, on the other hand, is bounded above by a and is monotonically non-decreasing. By the monotone convergence theorem, both sequences converge to a limit. This limit exists and this limit exists. But we can say more. We have this. If we take the limit as n tends to infinity of all sides, we get 0 less than or equal to, then we have limit n tends to infinity an minus limit n tends to infinity bn less than or equal to when we take the limit of this right-hand side as n tends to infinity. Because of the vector 2 to the minus n, this also goes to 0 as n tends to infinity. This means that it's not only that both limits exist, they are exactly equal. Both sequences will converge to the same point here between a and b. And we denote this limit by m of a comma b. This is the common limit of these two sequences. We can investigate some of the properties of this limit. If we start by two numbers that are exactly the same, then every arithmetic mean we compute and every geometric mean will be the same number a. So every sequence will be the constant sequence, and m of a comma a is equal to a. If we interchange a and b, we get the exact same limit. It is just that sequence b will be the non-increasing sequence and sequence a will be the non-decreasing sequence. If we allow the smaller number to be 0, I mainly talked about starting with two positive numbers. If we allow the smaller number to be 0, note that the geometric mean will be 0. So the b sequence will be the all 0 sequence, and what will happen is that sequence an will converge to 0. M of a comma b is m of a1 comma b1 is m a2 comma b2, and so on. Starting from a and b, we converge to this limit here. If we start from a1, which is a plus b over 2, and b1, which is square root ab, well, this is the second element in the main sequence. If we start from the second element, the sequence converges to the same limit. If we start from the third element, it's the same thing. Scaling a and b by some positive number, we get the same result, but it will be scaled by lambda. Again, this is taken from the fact that if we have a sequence Cn tends to C, then if you multiply by lambda, then lambda Cn converges to lambda C. Recall our goal. It is to evaluate this summation n in z of e to the minus pi n squared. We started by talking about a classical recursion, which is to start with two positive real numbers and keep replacing them by the arithmetic mean and geometric mean. We have discovered that by doing so, we construct two sequences that converge to what we called m a comma b. Now we turn our focus to something that also does not seem to be related to our objective, but then later this will actually be the tool that will allow us to get the value of this summation. This integral has two parameters, a and b, and again, without loss of generality, we can take a to be greater than b, which is greater than 0. We have integral d phi from 0 to pi over 2, and then we have 1 over square root a squared cosine squared phi plus b squared sine squared phi. We want to show that this integral remains the same if we replace a by the arithmetic mean of a and b, and if we replace b by the geometric mean. So our immediate goal is to show that I of a comma b is the same as I of a plus b over 2 comma square root ab, which means that I a0 comma b0, if a0 is a and b0 is b, this is I of a1, which is the arithmetic mean of these two guys, comma b1, which is their geometric mean. And if this is true, then this is also equal to I of a2 comma b2, where a2 is the arithmetic mean of a1 and b1, and b2 is the geometric mean of a1 and b1, and so forth. Note that the domain of integration is from 0 to pi over 2. On this interval, the sine function is strictly increasing. We will do a change of variables, but before doing it, let's investigate a particular function that will help us in proving the required result. This function is g of alpha equal to 2a alpha divided by a plus b plus 1 minus b alpha squared, and alpha is between 0 and 1. This function is strictly increasing on the closed interval from 0 to 1. Take the first derivative, g prime of alpha. So we apply the quotient rule. We get the square of the denominator, and upstairs we get 2a times the denominator minus 2a alpha times the derivative of the denominator, which is 2 alpha times a minus b. We can simplify the numerator of the first derivative. It is 2a, and then we have a plus b minus a minus b alpha squared. Note that alpha is between 0 and 1. So alpha squared is less than or equal to 1. Multiply both sides of this inequality by the negative quantity minus a minus b. We are assuming that a is greater than or equal to b. If we do this, we have minus a minus b alpha squared. Because we multiplied by a non-positive quantity, this inequality is reversed. On the right-hand side, we have minus a minus b. Add a plus b to both sides. We get a plus b minus a minus b times alpha squared is greater than or equal to a plus b minus a plus b. This is 2b, which is strictly positive. This means that the first derivative is strictly positive, and this is a strictly increasing function on the closed interval from 0 to 1. To show that this integral I of a comma b is I of a plus b over 2, comma, square root ab, we do the following substitution. We replace sine phi by 2a sine theta divided by a plus b sine squared theta. Recall from the previous page, we have this function with alpha between 0 and 1. We have proved that it is strictly increasing. Phi is from 0 to pi over 2. Theta is in the range from 0 to pi over 2. Sine phi and sine theta are from 0 to 1. This is a bijective function. To implement the substitution, the first thing, let's see what is cosine squared phi. If this is sine phi, then cosine squared phi is 1 minus sine squared phi. So we take this denominator and square it. And in the numerator, for cosine squared phi, we have the square of this quantity minus the square of 2a sine theta, which is 4a squared sine squared theta. Expand the square. This gives a plus b squared plus a minus b squared sine to the 4 theta. Then we have 2a minus b times a plus b, that's a squared minus b squared sine squared theta. The term a plus b squared, we can imagine it is multiplied by 1, and we can write down this one as cosine squared theta plus sine squared theta. From this square, we have now 4 terms, a plus b squared cosine squared theta, a plus b squared sine squared theta, then the square of this term, then 2a squared minus b squared sine squared theta. Let's combine the terms that have sine squared theta. From here, we have a plus b squared, so that's a squared, b squared plus 2ab. From here, we have 2a squared minus 2b squared. And from here, we have minus 4a squared. Those guys give minus a squared minus b squared plus 2ab. Taking minus 1 as a common factor, this is minus a minus b all squared sine squared theta. These 3 terms give minus a minus b squared sine squared theta. And then we have this guy, which is a minus b squared sine to the power 4 theta. We can take minus a minus b squared sine squared theta as a common factor. Then we have a bracket. In the bracket, we have 1 minus sine squared theta. And 1 minus sine squared theta is cosine squared theta. What we have right now is a plus b squared cosine squared theta minus a minus b squared sine squared theta cosine squared theta. Let's take cosine squared theta as a common factor. Multiply by 4 and divide this bracket by 4. This guy becomes a plus b over 2 all squared. Again, it's multiplied by 1, and we can write this one as cosine squared theta plus sine squared theta. Then from here, when we take cosine squared theta outside the bracket and then divide by 4, the remaining terms are sine squared theta and a minus b over 2 all squared. In this bracket, we have cosine squared theta multiplied by a plus b over 2 all squared. What about sine squared theta? Sine squared theta is multiplied by this term here, which is 1/4 a squared plus 1/4 b squared plus 1/2 ab. Then we have this minus 1/4 a squared minus 1/4 b squared plus 1/2 ab. We have cancellations, and the remaining factor to be multiplied by sine squared theta is 1/2 ab plus 1/2 ab, that's ab, and I can write this ab as the square root of ab squared. What we have here is cosine squared phi. If we go back to the expression used in the substitution, it means that cosine phi d phi is equal to the first derivative of this quantity. Imagining that we have alpha here, then by the chain rule, we have cosine theta d theta. We can divide both sides by cosine phi. This is the expression for cosine squared phi. We can take the square root and simplify. Using this, we have a relationship between d phi and d theta. In the integral of interest, we have this quantity a squared cosine squared phi plus b squared sine squared phi. We can replace this cosine squared phi by 1 minus sine squared phi. What we have is a squared minus, between brackets, a squared minus b squared sine squared phi. Sine squared phi is the square of this quantity here. We can combine these 2 terms. In the denominator, we have this square. In the numerator, we have this quantity. We can expand this square. It gives a plus b squared plus a minus b squared sine theta to the power 4. Then we have 2a plus b times a minus b sine squared theta, which is 2a squared minus b squared sine squared theta. Note that this term outside the square is exactly this term here, but rather than having plus 2, we have minus 4. These 2 terms together are like this term with minus 2, and so this means that we have a square like this one, but this plus sign is replaced by a minus sign. This is a squared cosine squared phi plus b squared sine squared phi. This is our original integral, I of a comma b. Now we have an expression for d phi, and we have an expression for this quantity. Using our results and simplifying, we get that this integral is integral from 0 to pi over 2 d theta, and then in the denominator, we have a square root, exactly like the original integral. Inside the square root, we have a plus b over 2 all squared times cosine squared theta plus square root ab squared sine squared theta. This is the same integral I, but the two parameters now are a plus b over 2 and square root of ab. I of a comma b is I of a0 comma b0. A0 is a and b0 is b. This is equal to I of a1 b1. This is a plus b over 2, and this is a square root ab. And then this is equal to I of a2 comma b2. a2 is a1 plus b1 over 2. b2 is the square root a1 times b1, and so forth. We have this important result that I of a comma b is I of an comma bn. An, which is the arithmetic mean, is always greater than or equal to bn, which is the geometric mean. In our integral, we have in the denominator an squared cosine squared phi plus bn squared sine squared phi. We can upper bound the integrand by replacing an by bn. So the integral I an comma bn is upper bounded by the same integral where this an here, because it's in the denominator, we replace it by the smaller bn, and so we get a higher value. If we do this replacement, we get an easy to evaluate integral. We can take bn squared as a common factor, and this will go outside as 1 over bn. Then we have integral from 0 to pi over 2. What is remaining in the denominator is cosine squared phi plus sine squared phi. That's 1. Thus our integral is pi over 2 divided by bn. We can lower bound this integral by replacing bn, which is here in the denominator, by the larger value an. If we do this, we get an integral that can be readily computed. We can take an squared as a common factor. It will get outside as 1 over en. In the denominator, we get cosine squared phi plus sine squared phi. That's 1. And the integral gives us pi over 2. I of an comma bn, which is I of a comma b, is lower bounded by pi over 2an and is upper bounded by pi over 2bn. It turns out that this integral here is very related to the arithmetic mean, geometric mean iterations that we have started with, in which we initialize a0 as a, b0 as b, and then an plus 1 is an plus bn over 2, and bn plus 1 is the square root of an bn. This integral here has a value that is lower bounded by pi over 2 times an and is upper bounded by pi over 2bn. We have studied both sequences. If we take the limit as n tends to infinity, the sequence an converges, the sequence bn converges, and both sequences converge to the exact same limit. If we take the limit of the left-hand side as n tends to infinity, we get pi over 2m of a comma b. If we take the limit of the right-hand side, we again get pi over 2m comma b. By the sandwich theorem, this integral is pi over 2 times m of a comma b. Let's evaluate the integral I of a comma b when a is equal to 1 and b is equal to 1 over square root 2. It turns out that this integral is very related to our summation of interest, sum n from minus infinity to infinity e to the minus pi n squared. This integral is from 0 to pi over 2 d phi over square root 1 squared times cosine squared phi plus 1 over square root 2 squared, that's 1/2 times sine squared phi. Rewriting this cosine squared phi as 1 minus sine squared phi, we get in the denominator 1 minus 1/2 sine squared phi. Our integral is from 0 to pi over 2 d phi, and here we have 1 minus 1/2 sine squared phi. Note that the function sine squared phi from 0 to pi over 2, it looks like this. It is symmetric about pi over 2. Our integral is exactly the same like integrating from 0 to pi and then dividing our result by 2. Our first substitution is the tangent half angle substitution. T is equal to tan phi over 2. D phi is 2 dt over 1 plus t squared, and sine phi is 2t over 1 plus t squared. Our integral is 1/2. When phi is 0, t is 0. When phi is pi, t is tan pi over 2, which is infinity. The integral now is from 0 to infinity. This is d phi, and this is sine squared phi. 2 goes with 2. We can take this guy and put it under the square root. So we have square root 1 plus t squared squared minus, we have 4 divided by 2, that's 2, and then 2 squared. This is 1 plus 2t squared plus t to the power 4 minus 2t squared. Our integral becomes from 0 to infinity. The integrand is 1 over square root 1 plus t to the power 4. Let's do another change of variables. Let y be equal to 1 over 1 plus t to the power 4. Note that if t is equal to 0, y is equal to 1, and if t is equal to infinity, y is 0. After doing the substitution, our integral will be on the interval from 0 to 1. We can express t in terms of y. Y inverse is equal to 1 plus t to the power 4. Y inverse minus 1 is t to the power 4. Raising both sides to the power 1 over 4, we have that t is equal to y inverse minus 1 to the power 1 over 4. We can write down dt in terms of dy, and then write our integral in terms of the variable y. We end up with this integral. Recall the beta integral. Beta m comma n is integral from 0 to 1, y to the power m minus 1, 1 minus y to the power n minus 1 dy. We need m and n to have real parts that are greater than 1 for this integral to converge, which is our case here, where we have m is equal to 1/4 and n is also equal to 1/4. This integral here times 1/4 is 1/4 times the beta function evaluated at 1/4 and 1/4. We know that beta m comma n is gamma m gamma n divided by gamma m plus n. Using this beta of 1/4 comma 1/4 is gamma 1/4 squared, and then in the denominator we have gamma 1/4 plus 1/4, that's gamma 1/2, which is square root pi. Our integral I of 1 comma 1 over square root 2, which is the integral from 0 to pi over 2 d phi over square root 1 minus 1/2 sine squared phi. This integral is equal to gamma of 1/4 squared divided by 4 times the square root of pi. Now it's definitely the time to start manipulating our summation of interest. Our sum is summation n from minus infinity to infinity e to the minus pi n squared, which can be written as summation n from minus infinity to infinity q to the power n squared, where q is equal to e to the minus pi. We will define function theta sub 3 of q, and generally q can be any complex number with a magnitude strictly less than 1. Theta sub 3 of q, by definition, is the summation n from minus infinity to infinity q to the power n squared. Our interest is theta 3 of e to the minus pi. We define another function, theta sub 4 of q, which is like theta 3, but it has this alternating term minus 1 to the power n, which is 1 when n is even and minus 1 when n is odd. Note that theta 3 of minus q is summation n from minus infinity to infinity minus 1 to the power n squared q to the power n squared, but minus 1 to the power n squared is the same as minus 1 to the power n, because n is congruent to n squared mod 2. N and n squared are both even or both odd. Thus, theta 3 of minus q is theta 4 of q. Let's sum these two functions. If we sum them, because of this minus 1 to the power n factor, we get double the sum with the even terms only. We can rewrite the sum from minus infinity to infinity and replace this n by 2n. In this case, we get 2 times the sum from minus infinity to infinity. What do we have? Q to the 4n squared, which can be written as q to the power 4 all to the power n squared. This summation here is theta 3 of q to the power 4. We have this result. If we add theta 3 of q and theta 4 of q, we get 2 times theta 3 of q to the power 4. What about theta 3 squared? What if we square this quantity here? We are squaring the sum from minus infinity to infinity, q to the power n squared. This becomes a double sum, n from minus infinity to infinity, m from minus infinity to infinity, q n squared times q m squared, which is q to the power n squared plus m squared. We rewrite the double sum as a single sum. What is the exponent? The exponent is a non-negative integer. We have here summation k from 0 to infinity, q to the power k. This is k. If we replace n squared plus n squared by k, the question is how many of those terms in the double sum are q to the power k, where k is some given non-negative integer. The term q to the power k in this double sum is repeated a number of times equal to r sub 2 of k. R sub 2 of k is a number theoretic function that tells in how many ways the non-negative integer k can be written as the sum of two squares. 0 can be only written as 0 squared plus 0 squared. So R2 of 0 is equal to 1. 1 is 1 squared plus 0 squared, or is minus 1 squared plus 0 squared, or is 0 squared plus 1 squared, or is 0 squared plus minus 1 squared. R2 of 1 is equal to 4. Note that when we counted the number of ways of writing 1 as the sum of two squares, we distinguished between order. We have considered that this is different from that. And the reason of this is that we have two summation indices here. We have a term in which n is 1 and m is 0. We have another term in which n is 0 and m is 1. Also, if 1 is replaced by minus 1, this should count as another term. Our indices here are integers and they can take negative values. R2 of k is the number of ways of writing the non-negative integer k as the sum of two squares. Sign and permutation are distinguished. If we square theta 4, this will be summation n from minus infinity to infinity minus 1 to the power n q to the power n squared whole square. We get a double sum n from minus infinity to infinity m from minus infinity to infinity minus 1 to the power n q to the power n squared minus 1 to the power m q to the m squared. This is minus 1 to the power n plus m q to the power n squared plus m squared. We can replace this n plus m by n squared plus m squared, because n squared plus m squared is congruent to n plus m modulo 2. If n plus m is odd, n squared plus m squared is odd. if n plus m is even, n squared plus n squared is even. We can write down the summand as minus 1 to the power n squared plus n squared, q to the power n squared plus n squared, and then rewrite the double sum as a single sum in which we replace n squared plus n squared by k. K is this non-negative integer that is expressed as the sum of two squares, but then we need to multiply by the number of times in which the term minus 1 to the power k, q to the power k appears. This is exactly the function r sub 2 of k. If we add theta 3 squared and theta 4 squared, we have this sum and we have the exact same sum, but with this factor here. Because of this factor, the odd terms in this summation are eliminated and the even terms are multiplied by 2. Theta 3 squared plus theta 4 squared is 2 times this summation here, r2 of k times q to the power k, but k is even. We can write k from 0 to infinity and replace each k inside the sum by 2k. The sum, theta 3 squared plus theta 4 squared, is 2 times summation k from 0 to infinity, r sub 2 of 2k times q to the power 2k. Claim r of k is equal to r of 2k. The number of ways to write down k as the sum of two squares is equal to the number of ways to write down 2k as the sum of two squares. Let's see why. Suppose that k can be written as alpha squared plus beta squared. Then 2k is 2 alpha squared plus 2 beta squared. This is not a square and this is not a square. However, we can write down the right-hand side as alpha plus beta squared plus alpha minus beta squared. This is the sum of two squares. For instance, if 5 is equal to minus 2 squared plus 1 squared, this is one way for writing down 5 as the sum of two squares. Based on this idea here, we can write down 10 as we have this plus that, that's minus 1, and we need to keep it as minus 1 squared. Then we have this minus that, minus 2 minus 1, that's minus 3. This way for writing 5 as the sum of two squares corresponds to this way for writing 10 as the sum of two squares. If 2k is gamma squared plus eta squared, note that 2k is an even number, so gamma and eta must have the same parity. They are both even or both odd, so that the sum is equal to an even integer. If 2k is gamma squared plus eta squared, then we can write k as gamma plus eta over 2 squared plus gamma minus eta over 2 squared. Each one of those guys is an integer because gamma plus eta and gamma minus eta are even. If we start with 10 written as minus 1 squared plus minus 3 squared, according to this, 5 is, we add these two guys and then divide by 2. Minus 1 minus 3 is minus 4 divided by 2, that's minus 2 squared. Then we have this minus that, minus 1 minus minus 3, that's 2, divided by 2, that's 1 squared. For every way for writing down k as the sum of two squares, there is a corresponding way of writing 2k and vice versa. We can find a bijection between the ways for expressing k and the ways for expressing 2k as the sum of two squares. The conclusion is the function r sub 2 of 2k is equal to r sub 2 of k. What is the benefit of this result here? We were at this step in which theta 3 squared of q plus theta 4 squared of q is 2 times this summation, r sub 2 of 2k, q to the power 2k. Based on this result, this is equal to r sub 2 of k. And q to the power 2k can be written as q squared all to the power k. What is this summation here? Summation k from 0 to infinity. Then we have r sub 2 of k. Then q squared, something here to the power k. That's exactly the square of function theta 3. Specifically, this is theta 3 of q squared squared. The conclusion is that theta 3 squared of q plus theta 4 squared of q is double theta 3 squared of q squared. Dividing both sides by 2, we find that theta 3 squared of q squared is the arithmetic mean of theta 3 squared of q and theta 4 squared of q. Let's study this product. Alpha times beta can be written as 1/2 alpha plus beta squared minus 1/2 alpha squared minus 1/2 beta squared. Theta 3 of q times theta 4 of q, 1/2 the sum squared minus 1/2 the square of this guy minus 1/2 the square of this guy. This summation here divided by 2 is theta 3 of q squared squared. What about the sum of these two thetas? The sum is 2 theta 3 of q to the power 4. When we square this, we get 4 theta 3 squared of q to the power 4. 4 divided by 2 is 2, and then we have theta 3 of q to the power 4 squared. What about this quantity here? We proved this result. Replace each q by q squared. Left hand side becomes theta 3 of q squared squared, that's q to the power 4 square. On the right hand side, these two q's become q squared. This means that 2 times this quantity here is this sum, theta 3 of q squared squared plus theta 4 of q squared squared. This goes with that. We are left with theta 4 of q squared squared. This is this product. We can write down this product as the square root of the squares. What do we have? We have theta 3 of q squared and theta 4 of q squared. For simplicity, let's just assume that q is a positive real number. Q is in the open interval from 0 to 1. These are real valued positive quantities. We have proved that theta sub 3 of q squared squared, this is the arithmetic mean of these two quantities. And theta sub 4 of q squared squared, this is the geometric mean. We can keep doing this. Theta 3 of q to the power 4 squared is the arithmetic mean of these two guys. And theta 4 of q to the power 4 squared, this will be the geometric mean. And so forth. If we play the AMGM iteration game starting from these two guys with argument q, we get them with q squared. If we take another step, we get them with q to the power 4, and so forth. At the very beginning, we found that m of a0, b0, where this is a and this is b, is equal to m of a1, b1 is equal to m of a2, b2. What is the limit point of these sequences? Theta sub 3 of q to the power 2 to the power k, this is summation over integer n of q to the power 2 to the power k n squared. As k tends to infinity, the terms here approach 0, with the exception of the term at small n equals 0. This remains equal to 1. Theta 3 of q to the power 2 to the k approaches 1 as k tends to infinity. The same applies to theta 4. This sequence with index k also approaches 1 as k tends to infinity. The conclusion is that m of theta 3 of q squared, theta 4 of q squared, this is equal to 1. By taking a common factor, theta 3 of q squared, we have that theta 3 of q squared times m of 1 and theta 4 of q squared divided by theta 3 of q squared. This is 1. Then theta 3 of q squared is 1 over m of 1 and theta 4 of q squared divided by theta 3 of q squared. This is what we need. Our main goal is to obtain theta 3 of e to the minus pi. This is a formula for theta 3 of q squared. It requires that we evaluate this quantity here. We know that there is this integral I of a comma b, which is integral from 0 to pi over 2 d phi divided by square root a squared cosine squared phi plus b squared sine squared phi. We found that this integral is pi over 2 times m of a comma b. This means that 1 over m a comma b is 2 over pi times the integral. Thus, we can represent the theta function in terms of this integral that we studied earlier in this video. Theta 3 of q squared is the reciprocal of m of 1, and then we have this parameter. This is a number less than 1. The summation for theta 4, it has this minus 1 to the power n, while the summation for theta 3, when q is a positive real number between 0 and 1, all the terms are positive. If we are interested in this quantity here, then we can write it in terms of this integral. Specifically, theta 3 of q squared is 2 over pi, and then the integral. Cosine squared of phi is multiplied by 1. Sine squared of phi is multiplied by the square of this quantity. So this will be theta 4 of q to the power 4, and in the denominator we have theta 3 of q to the power 4. Further, we can write down this integral by replacing this cosine squared of phi by 1 minus sine squared of phi, and we can combine the terms with sine squared of phi. This is an integral representation of the function theta 3 of q squared. It is not clear that we are done or that we have achieved anything, because what is this ratio when q is equal to e to the minus pi or some other value of interest? This function here now is represented as an integration, but to be able to evaluate this integral, we need to obtain this ratio here of the fourth powers. We still have some work to do. We are interested in this ratio, and to be focused, our main interest is when q is equal to e to the minus pi. To get ahead of myself, we will discover that this ratio is equal to 1/2, and so 1 minus 1/2 is 1/2, and we end up with the integral that we have evaluated earlier. Let's assess our current situation. We defined this function theta3 of q as summation n in the integers of q to the power n squared, and theta4 is the same thing but with minus 1 to the power n. And let's take q to be a positive real number in the interval between 0 and 1. Using the definitions, we discovered the following: theta3 of q squared and theta4 of q squared. If we take their arithmetic mean, this is theta3 of q squared squared. If we compute the geometric mean, then this is theta4 of q squared squared. If we compute the arithmetic mean again, we get theta3 of q to the 4 squared. If we compute the geometric mean, we get theta4 of q to the 4 squared. If we compute the arithmetic mean, we get theta3 of q to the 8 squared. If we compute the geometric mean, then we get theta4 of q to the 8 squared, and so on. Each one of those guys is obtained from the previous step by computing the arithmetic mean and geometric mean. This is exactly like the EMGM iterations we have studied at the very beginning. We already have the result that if we do these iterations, we obtain converging sequences. The top sequence and the bottom sequence, both of them are convergent. And the quantity that is m of theta3 of q squared, theta4 of q squared, this quantity remains the same if we compute it using these two guys, or these two guys, or these two guys, and so forth. As we move forward in our iterations, we can actually investigate the limit. Q is raised to higher and higher powers. If q is a real number between 0 and 1, then q to a higher and higher power of 2 gets smaller and smaller, and both of these sums will converge to 1. Thus, this m here, whether we use q or q squared or q to the power 4 or q to the power 8, this m is equal to 1. Okay, so what is the benefit of doing something like this? This m is related to an integral. This was the second part of this video. We started by investigating the iterations, and then we moved towards the integral. In our particular case, this m is equal to 1. And this m is equal to theta3 of q squared times m of 1, comma, theta4 of q squared divided by theta3 of q squared. Consequently, theta3 of q squared is 1 over this m of 1, comma, the ratio of the second powers, theta4 divided by theta3 squared. This has an integral representation. This is 2 over pi, integral from 0 to pi over 2, d phi divided by square root. Then we have this guy squared times cosine squared phi plus this guy squared times sine squared phi. We can write down cosine squared phi as 1 minus sine squared phi, and we have 1 minus, then we have the ratio theta4 to theta3 raised to the power 4, and then we have sine squared of phi. We do have an expression for theta3 of q squared, and our interest is the case when q is e to the minus pi, but our integral, unfortunately, needs this ratio. For our problem, we need theta4 of e to the minus pi divided by theta3 of e to the minus pi raised to the power 4. As you can see, we still need to do more. And our next step is the Jacobi identity. We need one more relation between those functions so that we can assign a value to this ratio. Let's investigate this difference. The difference between this guy and this guy. Theta3 of q squared minus theta3 of q squared squared. We know that the theta function is a single sum. We square it, we get a double sum, and the double sum will have q or q squared in this case, and then we have m squared plus n squared, where these are the summation indices. And then we can do this trick of writing down the double sum as a single sum using this function, which gives us the number of ways in which some non-negative integer can be written down as the sum of two squares. And we need to respect order, and we need to respect sign. The difference between these two sums is just that in one of them we have q, in the other one we have q squared. On the previous page, we spent some time to argue that the function r sub 2 of k is equal to r sub 2 of 2k. Let's exploit this result here. Specifically, we will take this summation and replace this r sub 2 of k by r sub 2 of 2k. Both sums have the index going from 0 to infinity, but here we have k and k. Here we have 2k and 2k. This summation simply includes the even index terms in this summation. If we compute this difference, we end up with this summation, but over the odd k. And it is better to have an index, let's say v, from 0 to infinity, but we replace this k here and k there by 2v plus 1, and then q to the power 2v plus 1. So far in this video, when we deal with the squares of the theta functions, convert the double sum into a single sum using the R function. Now we will actually move in the reverse direction. We will take this single sum and rewrite it as a double sum. We have summation k from minus infinity to infinity, summation m from minus infinity to infinity, then we have q to the power k squared plus m squared. This is not enough. The numbers that we have here that are represented as sum of two squares, those numbers are odd. We must have k squared plus m squared being odd. Alternatively, k plus m must be odd. One of those indices is even, the other must be odd, and vice versa. Let's do a change of summation indices. We have, again, k is an integer, m is an integer, and k plus m is odd. We change from k and m to I and j, where I and j are just integers, but we will use k equal to I minus j and m equal to I plus j plus 1. By doing this transformation, note that if we add k and m, we get 2i plus 1. This is guaranteed to be odd. Rather than having a double sum where k is in z, m is in z, and the sum is constrained to be odd, now we have a double sum in which I is in z, j is in z, and that's it. Given this, k squared plus m squared that we have in the exponent is I minus j squared, that's I squared plus j squared minus 2ij. Then we have n squared, this will give us I squared and j squared and 2 plus 2ij, but then we have also plus 1 plus 2i plus 2j. When we add, these two guys cancel, we have 2i squared plus 2j squared plus 2i plus 2j plus 1. Take 2 as a common factor, this is 2. We have I squared plus j squared plus I plus j plus 1 half. What we have here inside the bracket can be written as I plus 1 half all squared. This will give us I squared plus I plus 1/4. And then we have j plus 1 half squared. This will give us j squared plus j plus 1/4. This double sum here is summation n from minus infinity to infinity, q to the power 2, then we have n plus 1 half squared, and the sum is squared. If we square this summation, we get exactly this double sum. This is a function in which we have the summation from minus infinity to infinity q squared to the power not n squared, but n plus 1 half all squared. This is different from the function theta 3, in which we raise to the power n squared, and theta 4, in which we raise to the power n squared, but then outside here we have minus 1 to the power n. So we need to define a new function, and this function is theta 2 of q. It is a function in which we take q and raise it to the power n plus 1 half all squared. In terms of this function theta sub 2, what we have here is theta 2 of q squared squared. Theta 3 of q squared minus theta 3 of q squared squared is this new function, which is theta 2 of q squared squared. This is the result that we have. We know that theta 3 of q squared squared is the arithmetic mean of these two guys. So this sum is equal to 2 theta 3 of q squared squared. We can move this to the other side. In other words, we can write down theta 3 of q squared, which is this term here, as 2 theta 3 of q squared squared minus theta 4 of q squared. If this is replaced with this, and then we subtract this guy, this minus theta 3 of q squared squared will reduce this 2 to 1. Now we have theta 2 of q squared squared is theta 3 of q squared squared minus this guy, theta 4 of q squared. We can move this to this side, and we can move this to this side. Theta 4 of q squared is this difference, theta 3 of q squared squared minus theta 2 of q squared squared. Let's go back to this line here and square both sides. This becomes theta 2 of q squared to the power 4. On the right hand side, we get the following. We get theta 3 of q squared to the power 4 plus theta 4 of q to the power 4. Then we have minus 2, the product, theta 3 of q squared squared, theta 4 of q squared. Let's recall our previous results. Theta 3 of q squared, theta 4 of q squared. The arithmetic mean is theta 3 of q squared squared, and the geometric mean is theta 4 of q squared squared. Here we have double theta 3 of q squared squared, double the arithmetic mean. This is simply the sum of these two guys. I can write down this as theta 3 of q squared plus theta 4 of q squared. And this is multiplied by theta 4 of q squared. We have theta 3 of q squared to the power 4 plus theta 4 of q to the power 4. minus theta 3 of q squared, theta 4 of q squared. Finally, we have minus theta 4 of q to the power 4. We have cancellation. This goes with that. Now we have this product here from our previous result. This is the geometric mean of these two guys, which means that if we have the product theta 3 of q squared, theta 4 of q squared, this will be theta 4 of q squared to the power 4. Our expression becomes theta 3 q squared to the power 4 minus theta 4 q squared to the power 4. If we take this equal to that and square both sides, the left hand side is theta 2 of q to the power 4. Now we have shown that the right hand side is theta 3 of q to the power 4 minus theta 4 of q to the power 4. For our specific case, in which q is e to the minus pi, this means that this summation raised to the power 4 is this raised to the power 4 minus that raised to the power 4. Recall that this is our situation. We are interested in getting this ratio theta 4 to theta 3 raised to the power 4. Hopefully, if we get this with q equal to e to the minus pi, we are able to evaluate the integral and then obtain this theta 3 of q squared. We just take the square root and we arrive at our desired result. But what we have is not the ratio. We ended up with this expression involving the fourth powers. In fact, we have a new function that has entered into the picture. Rather than obtaining the ratio of theta 4 to theta 3, now we have this new function involved. How can we use this to obtain theta 4 of e to the minus pi divided by theta 3 of e to the minus pi to the power 4, so that we insert it in the integral and hopefully evaluate the integral and obtain our friend here? It turns out that in our case, this theta 2 of e to the minus pi is exactly that, theta 4 of e to the minus pi. How can we show this? We can employ the Poisson summation formula. Suppose that you have a function g of t, and we have big G of f is the CT-ft of g of t, the continuous time Fourier transform. This is the integral from minus infinity to infinity, g of t e to the minus I 2 pi ft dt. A special case of the Poisson summation formula tells us that if we evaluate this function at the integers and sum, and we evaluate this function at the integers and sum, under some conditions, we have equality here. The function e to the minus pi t squared is an eigenfunction of the continuous time Fourier transform. The CT-ft of this function is e to the minus pi f squared. The integral of this function after multiplying by e to the minus I 2 pi ft is a classical contour integration in the complex plane. It will give us that the Fourier transform is e to the minus pi f squared. Suppose that we multiply our function by e to the minus I by t, e to the minus pi t squared. We have a general rule. If g of t has the continuous time Fourier transform g of f, then if we take g of t and multiply by e to the minus I 2 pi f0 t, then we have a shift in the frequency domain. We get g of f plus f0. And this is clear from the integral. If we multiply g of t by e to the minus I 2 pi f0 t, this will be combined with the kernel of transformation, and we end up with f replaced by f plus f0. So this is the rule. Let's apply it here. E to the minus pi t squared, it has a Fourier transform e to the minus pi f squared. If we multiply by e to the minus I pi t, this is exactly e to the minus I 2 pi 1/2 t. It's like f0 is equal to 1/2. According to this rule, then the Fourier transform is e to the minus pi, and then we take this as a shift in the frequency domain. The CT-ft of this is e to the minus pi f plus 1/2 squared. This is the CT-ft. But what if we apply the Poisson summation formula? The Poisson summation formula tells us the following. We have two sums that are equal. This sum, when we replace f by integer n, e to the minus pi, n plus 1/2 square, this is equal to this guy here after replacing t by an integer n. So here we have e to the minus I pi n e to the minus pi n squared. What is this summation? This is summation over integer n e to the minus I pi, that's minus 1. This is minus 1 to the power n e to the minus pi n squared. This function is theta 4 of e to the minus pi. This function is theta 2 of e to the minus pi. In our particular case, these two guys are the same. This and this are the same. Theta 3 of e to the minus pi to the power 4, if we move this to the other side, is equal to 2 times theta 4 of e to the minus pi to the power 4. This means that theta 4 of e to the minus pi divided by theta 3 of e to the minus pi, this ratio raised to the power 4 is 1/2. This is the number that we needed here. In our case, this is 1/2. If this is 1/2, 1 minus 1/2 will give us this integral. We carried out this integral on page 5. It is gamma of 1/4 squared divided by 4 times the square root of pi. This is theta 3 of e to the minus pi squared. The sum of interest, the sum we have been hunting for, is the square root of this quantity. The summation here is gamma of 1/4 divided by 2 to the power 1/2 pi to the power 3 over 4. This is our desired result. In addition to this result, we actually have a family of results. If we know this guy, we know that theta 4 of e to the minus pi divided by theta 3 of e to the minus pi, this is equal to 1 over 2 to the power 1 over 4. Now we know this, so we know this theta 4 of e to the minus pi, which is this sum, but with minus 1 to the power n. Knowing these two guys, we know their squares. And knowing their squares, then we can compute the arithmetic mean and the geometric mean. We can obtain theta 3 of e to the minus 2 pi square and theta 4 of e to the minus 2 pi square. Those are sums that look like this, but rather than having e to the minus pi n square, we have e to the minus 2 pi n square, and so on. The final thing to say is that we can also extend our results thanks to the Poisson summation formula. We have e to the minus pi t squared has a continuous time Fourier transform e to the minus pi f squared. What if we multiply t by a positive real number alpha? The scaling rule of the continuous time Fourier transform tells us that the Fourier transform is 1 over alpha e to the minus pi f over alpha squared. If we choose alpha to be square root of 2, then the continuous time Fourier transform of e to the minus 2 pi t squared is 1 over square root 2 e to the minus pi f squared over 2. Applying the Poisson summation formula, we have summation e to the minus 2 pi n squared, where n is an integer, is equal to 1 over square root 2 summation e to the minus pi n squared over 2. If we obtain this sum, then we can obtain this other sum. The idea is it is not just that we have obtained this summation. The framework of the theta functions and the Poisson summation formula will allow us to generate so many results just based on this result here.